prove that the active circuit shown here is a difference amplifier with a relationship between the output Vout shown here and the difference of the two input voltages V1 and V2 in such a way that the difference gain is the one that is shown in red color here. Okay, so to get to this, let's quickly just see what's going on in the circuit. We have three op-amps, ideal op-amps, and we are making the assumption that they are properly biased, and as you can see, all of them, the three of these op-amps are actually with negative feedback. So I'm making the assumption that they are properly biased so that all of the three op-amps are in linear region of operation, not saturated. So virtual short is valid for the three op-amp. So with virtual short in place, I'm saying voltage at positive input terminal for each op-amp is equal to voltage at negative input terminal. So when we have V1 here, we have V1 also here. When we have V2 here, we have V2 at this node as well, which means this node. All right. So one way of dealing with this problem is using superposition, meaning that one time assume V1 is there, but V2 is 0, and find the contribution to the output, and another time assume V1 is 0 and just find the contribution of V2. That's one way, but let's make it, it's actually not difficult to figure out the answer while we assume both V1 and V2 are in place, and we just write simple KCLs. So I am going to write one KCL here at the negative input terminal of op-amp 1. So this is op-amp 1, this is op-amp 2, and as you can see, op-amp 3 is just a buffer. So for that, I'm not worried. Whatever I find here will be the same as what I find at the output. Okay, so KCL at, let's say, negative terminal, input terminal of op-amp 1. Okay, so to do that, you can see what's happening is one current is going this way, another current is going this way, and these two currents, they add up together and they become the current that is going through R2, because nothing can go through the input terminal of ideal op-amp with infinite impedance. So let's just write the KCL. So if I refer to this node as Vx, the voltage at that node, if it is Vx, I can write this way. I have V2 here, and as you can see, I have V1 here. So therefore I can say, let's say current I, just put a name there. Let's say current I1, and let's say current I2, and let's say current I3. So I have I1 plus I2 is equal to I3. So in that case, I1 is simply V2 minus V1 divided by R. I2, which is going through R1, is Vx minus V1 divided by R1. And I3, which is the one going through R2, is simply V1 minus 0 divided by R2. Okay, so let's refer to this as equation 1, but what I'm going to do is, let me reshuffle things around in this equation 1 so that I find Vx as a function of the rest of the voltages. So I'm going to change the color so that we have better contrast. I can write it this way. Vx over R1 is equal to, or let's put it this way, negative Vx over R1 is equal to V2 minus V1 divided by R. So I'm just moving Vx over R1 to the other side so that it becomes negative Vx over R1. And then I have negative V1 over R1 and negative V1 over R2. Okay, so let's keep this as equation number 1. Now, let me change the color so that you can see better. I am going to write KCL at this node. Okay, so that's now, let's write KCL at negative terminal, input terminal of op-amp number 2, this op-amp. Okay, so if we do that, you can see we have this current, which we refer to that current as, let's say, let me put it this way so that it's less busy. So the current going through this resistor, let's name it I4. I can write I4 should be equal to, nothing can go through the input terminal of op-amp. So all the I4 should be either going through as I1 or this way. Okay, so I4 should be equal to, I1 is V2 minus V1 divided by R, and the second component is what is going through R1. Obviously that's V2 on one side of R1 minus Vx on the other side of R1 divided by R1. Okay, great. I4 is Vout divided by V2 on two sides of this R2 resistor divided by R2. So I am going to just write it as, so I'm going to substitute for I4 as Vout minus V2 divided by R2. Great. So what is happening is if I reshuffle things around, I can leave negative Vx over R1 on one side, and I can move everything to the other side. By that, I mean I can say is equal to negative V2 minus V1 over R. So I am moving this component to the other side of equation. I am keeping negative Vx over R1 this side, moving everything to the other side. So it becomes negative V2 over R1 and negative V2 over R2, and finally plus Vout over R2. Okay, this is equation number 2, and obviously comparing equation 1 and 2, you can see I can set them on one side, both of them, they are equal to negative Vx over R1, so I can set the right hand side of these two equations equal to each other. So let me change the color so that we have good contrast. From 1 and 2, I can say, therefore, V2 minus V1 over R, and I'm going to simplify the whole thing. So this is times 2. And so again, I am setting the right side of the equations 1 and 2 equal to each other because the left side is the same, negative Vx over R1. So as a result, what I can write is 2 times V2 minus V1 over R minus V1 over R, R1 minus V1 over R2, that's from equation 1, is plus V2 over R1 plus V2 over R2 is equal to Vout over R2. Okay, so let's multiply both sides of this final equation by R2 so that we get rid of R2 in denominator of Vout. Become Vout is equal to, so Vout is equal to, as you can see, we get V2 minus V1 factored out, and then we have 2 times R2 over R1 over R, so 2 times R, and then as I said we are multiplying with R2, and then we have V2, we have V2 minus V1, which is factored out, and it becomes R2 divided by R1, and finally become R2 divided by R2, which is 1. That's exactly what we wanted to find. exactly matching what is asked to be proven in this question. So yes, we managed to show that Vout is simply related to the difference of the two input voltages. It's not as if we have separate gain that are different for each of the voltages. This is a pure difference amplifier because the output is defined by a gain, which is this gain, the difference gain. Let me highlight it with different colors so that it's easy to be seen. So this is the difference gain of this difference amplifier. So this is the gain. And you can see that the output is purely defined as the difference of the two input voltages times a gain. So it's just done. That is exactly what we wanted to prove. I hope that this is helpful.